So you guys, I wanted to go ahead and make a video now to cover what we did yesterday in our presentation that I posted on Beachboard. Today's going to be a little bit different in that I'm just going to let the Vivado tool place the files where they want to. So I'm not going to worry about that. But the first thing we do want to do is to make sure that we have a directory set up, that we are ready for our project to be stored there. So today we'll call this project 1 201 video. So now we're going to go in, now that we've got the directory set up, we're going to say create a new project. And Vivado's response time isn't always the best, but it's not too bad. So it's going to walk us through. We're going to call this project 1 201 video. And then we get to choose exactly where we put it. So my directory is here on W. We're going to go into 201, and I'm going to choose the directory we just set up. We want it to be an RTL project. This time we're going to say we want to specify our sources. So again, we have to choose our board. So the first thing we'll do is select boards. We're using the Nexus A7 100T, so we select that. And now we say, okay, we're ready to go for you to create our project. And we'll wait for a moment while he gets everything ready and opens up the Vivado display. So I'm going to make this a little bit bigger here. Let him finish what he's doing. But we can begin to look to see we've got the area where we have to deal with our project. IP stands for intellectual property. That refers to the files that you create, or you may use other people's IP, or you may use the tool to generate IP for yourself as well. We have the simulation area where we run our simulations, as we saw yesterday. And the synthesis is where we make sure we're ready to go to our board, and then the implementation will go to our board. So let's go ahead and make this larger so we're not looking at anything other than our screen that we're working with in front of us. So now we want to add sources. So we'll say add source. We want to add or create a design source. We'll start with the design that we're working with first. And then we'll say create a file. It's going to be a Verilog. And let's call this project 1 201. We'll just call it video. We'll have it local to the project. Like I said, we're going to let him put it. It's a Verilog file. You can see we could also create system Verilog or VHDL or some other files. But for us, we're just going to use Verilog. Say OK. Now we're going to say finish. Now he's going to say, OK, I'll help you create your file. Now, what you have to tell me is what the ports are to your file, whether they're inputs or outputs, whether they're vectors or scalar. It comes up with no check, so that means our first input will be a scalar. Let's call it A. Our second input will be B, also a scalar. Our third input will be C, also a scalar. Our fourth input will be D, also a scalar. Now we want to specify our output. So we say Y, But we then come to the direction, we select and we say make Y an output. In this case, everybody is 1 bit wide. Once we've identified all the ports, now we say OK. He will go ahead and create the file. Nothing changes, but you can see in the project manager under design sources, you can see our file. So now if I double click this, he opens it up for us to edit. Now, admittedly, I don't remember exactly the same expression we used yesterday, but let's go ahead and create a file. That'll be very simple. So this time, we'll say register Y. That's, let me come down and add a comment. So we want to define the output. Now we will implement our design using a procedural block. So now we'll say always at asterisk. Since we're going to have more than one statement, we'll use the keyword begin. Now we want to, and I'm going to have to go back and change. So let me do this what I did yesterday. So now I want to say define the intermediate values. And let's have a reg, we'll call it T1, T2. So in our design, we want T1 to equal A exclusive OR with B. And we'll let T2 be equal to not C and D. And finally, we'll say Y is equal to T1 or T2. Then we say end. We have the end module. Notice that the tool helps you out. As you're typing, the little red squiggly line shows up. So let me just put another letter here, end R. That is incorrect. When you're trying to debug your designs, oftentimes you'll see an error indication. He says something's wrong. I'm at the end module, but something happened on my way here. He doesn't know exactly what's going on. So oftentimes when you see an error reported on a particular line number and you look at that line number, it may be beautiful. Everything may be good. So then what you should do is go back up in your source code to see where your mistake is. In this case, obviously, it's our end R. I correct it, and now he says that he doesn't see any obvious errors. So let's go ahead and save this by clicking the save icon here. Now, just like yesterday, I'm going to go ahead and copy this. To use it when I get into my test fixture. Now we want another new source. So we go back to add source. This time we say we want to add or create a simulation source. So we're going to create a file, and we want the file name to be the same as our file, project1 underscore 201 underscore video underscore TF. So when we create our simulation file or our test fixture, we always put use the same name as the design we're testing, but we follow it with an underscore TF so we know that is our test fixture file. And we can say OK, and now we're done. So now we're at the same spot. The tool should know that this is a test file, so we don't have ports. So we know we don't have ports. So we're just going to say OK. He's going to say, oh, you have no ports. Are you still happy? And I'm going to say yes. So what will happen is he will create my simulation source. You don't see it directly here, but he says, okay, this is your first simulation exercise. So I'll put this file here underneath simulation 1. Now I'm going to double click on the test fixture here. Now we see our test fixture with nothing in it. So I want to start to clean it up. Now I know, let me go ahead and paste in this part from my previous. So I know that I've got 4 inputs and 1 output. So in my test fixture, I need to define 4 inputs. I call it TA for test A, just to make sure we can see in the syntax how we reference our design within our test fixture. I'm going to say test B. I'll say reg test C, reg test D, and then we'll say wire test Y. Now, why is it a wire? The registers are the values that we're going to provide to the inputs of our design. Therefore, we need registers to assign values to them in order to have them be the inputs to our design. The design will respond to our change of our inputs by generating the output Y. That's why we call our test Y a wire. So if we're assigning a value to it in our test fixture, it must be a register. What is coming back to us from our design will be a wire. So now let's go ahead and I'm going to change this. So we'll give it, this is the name of the module we're instantiating. Now we'll give it an instance name, and that just allows us to reference our design. We want to get rid of the words input. Get rid of the word output. Now we want to say to port A, I want to connect test A. Then we'll say to port B, I want to connect test B. Then we'll say to port C, I want to connect test C. Then we'll say to port D, I want to connect test D. And finally, for our output, to port Y, I want to connect test Y. And then we don't put a comma at the last one, but we do close it out with a parenthesis and a semicolon. So I'm going to come back up and I'm going to add a note. We want to instantiate the device under test, commonly referred to as a DUT, the device under test. So we've declared the variables that we need. Let's go up and go ahead and put a comment here as well. So now we are declaring the required variables. We instantiate our device under test. Now we want to come in and provide our stimulus. So we want to use an initial block. We'll say begin because we have more than one statement. We want test A to start up as a 0. We want test B to start up as a 0. We want test C to start up as a 0, and we want test D to start up as a 0. Now, as always, I like to use a integer in my test fixture, so I'm going to come up and declare the integer I, and that'll make our test fixture a little easier to implement. Then I want to say wait 50 time units. Now, how do we interpret 50 time units? We go all the way back up to the top of the file, and we see the time scale. This is what you would call a compiler directive. The tick here is the accent grave. It's the upper left part of your keyboard, not the one next to the enter key. Then we have the keyword time scale. And what it does is it tells the simulation how to interpret references to time. This is a reference to time, pound 50. That says wait 50 time units. And what is our time unit? Our time unit is 1 nanosecond. So that means when I say pound 50, I want it to wait 50 nanoseconds. The slash 1 picosecond, the picosecond is the precision. That means if I wanted to, and we don't often need to, I could have defined time to be 50.123 nanoseconds because my precision is 1 picosecond. So of course that's 123 picoseconds. So I'm able to define a delay as fine as picoseconds. But for us, we are happy with just dealing with the integer value of the nanosecond. So now we want to have a loop. In the initial block, as well as the always block, since it's a procedural block, we're able to use some procedural constructs. So we can use a for loop. So we'll say for I equals 0, I less than 16, I equals I plus 1. Now, nobody likes I equals I plus 1. C very nicely made this I plus plus, but that does not work in Verilog. For us, we use I equals I plus 1. So what am I doing? I want to now wait 50 time units, and now I'm going to switch my inputs. So I'll use a concatenation operator, which is the curly brackets. That means I want to treat A, B, C, and D syntactically as one object. And I want to assign to it the 4 LSBs of I. So what I've done is I is an integer. The integer is 16 bits wide, so it goes from 0 to 15. I only want to use the 4 LSBs. So what I'm going to do is each iteration, I'm going to assign a unique value to ABCD. This value will range from 0, 0, 0, 0 through 1, 1, 1, 1. And we'll see all of the values applied to our design. Now, just from a quirkiness in the waveform display, I'm going to make one more assignment. So I'm going to say wait 50, and then I want to say A, comma B, comma C, comma D equals 4 bits of 0. And now the last thing I need is my end. So I have an initial, begin, and an end. This is the sequence that I'm going to use to drive my test. What am I testing? I'm testing the device under consideration, the device under test, project 2 video. I then itemize all of the ports, and then I connect the signals from my test fixture. So let's go ahead and save our test fixture. Now I hope I do this without errors, but we'll find out. It looks like he may have an error. Let's see if he tells me what it is. So let's run the simulation, we'll find out. So let's come here. Now we're done with the creating of it. Now we want to simulate. Simulation settings. We want to use the Vivado simulator. All of this, our top level module name. We want to make the test fixture. We say OK. Now let's go ahead and run our simulation and we'll see what he thinks. Oh, there's an error. So let's come down to the Tickle console. And what does he tell us? Here. There's an error in our file, line 43. So if I come over to our file, let's see if we can figure out what's going on. That looks pretty good to me. Oh, test fixture 47. Let's go there. Oh, I don't see what the error is. Syntax. Oh, look at that. Sometimes these are tough. INITIAL. Initial. So let's save that. Let's run our simulation again. Ah! Test fixture 47. Oh, this is turning out to be bad. A is not declared. Oh, I got it. It's just good. Test A. Test B. Test C. Test D. So it's always good to have a game plan, have it all written out. I'm making a mistake in front of everybody, but I'm not too proud. So let's try it again. Now we want to run the simulation. Okay, so now he likes it, so we should get a clean run. We should then enter into the simulation. So when it shows up, basically the tool automatically will select a period of time to run a simulation for. It will show the tail end of that run. So we can come here and we see we have some options here. One is to zoom in, zoom out, zoom fit. Let's press zoom fit. That will give us the whole layout. We don't care about because we're using the 3 LSBs. So let's go ahead and get rid of I. And now we can look and see the input and the outputs. Now, one of the things we can do, we can select the inputs. We could change the color if you like being able to see different colors. So now my inputs are all yellow. Let's go ahead and make my output pink. So now I see very clearly these are my inputs, this is my output. Once I place the cursor, it'll show me where the cursor is. Then you can use the up arrows to change from one signal to the next, or you can use the right arrows to move the cursor to the next transition on the right. So here, every place D changes, I go to the right with the right arrow key, to the left with the left arrow key. If I come down to my output, it will jump to where my output changes. So this is very helpful when you're walking through your designs and you want to find the next transition. Now for us, we only have scalars, but let's show one other option that is very helpful. We can go to what's called the radix. Now since it's a scalar, it doesn't show up. But if it was a vector, we would see we could display it as an unsigned decimal, signed decimal, or hexadecimal value. That's very helpful when dealing with larger variables, meaning vectors as opposed to scalars. So this pretty much covers what we did in the presentation. The nice thing about this presentation is you're able to stop it and go ahead and check out what you're doing. So hopefully we're all able to get into these and are beginning to warm up to the use of Vivado and its how we program it and how we go. So we still need to introduce the idea of generating the file for the programmer. We'll start that next week.